is more likely to be attracted to the carbon that carries a higher positive charge. So it's going to be attracted more likely to this carbon than to that. If you want to draw it this way, that's okay. The other way is simply to draw it and say, okay, this resonance structure is more important than the other resonance structure. So the real molecule is more like this one than this one, and the bromide ion then simply comes along, and this is the preferred, the kinetic preferred product. Okay? So that's reasonable. I mean, it makes decent sense that if there's a high amount of positive charge on one carbon, the bromine would like to go there faster, more readily than to the one where there's a less amount of positive charge. So what about the next idea? Can we explain, or does it make sense about the thermodynamic stability? So let's look at the thermodynamic stability of the products. Products and the equilibration process. Let's do the first one. So we have CH3 at 40 degrees. We have an allyl system. The bromine is a good leaving group, it comes off. So it goes to back where it started from, and it comes off pretty readily. It's on an allyl carbon and even a secondary carbon as well. So minus the bromine gives you then the carbocation. And remember, you can draw it in two ways. I'm not going to draw it the second way this time. And if that the same thing, to go back, you simply add bromide ion again. So to go back, you add bromide ion. If in the other direction, if we add Br minus at this carbon, push the electrons over, we then end up as that, and that compound, if you take away bromide ion, it will go back. So this is the shuttle, the intermediate that allows you to go from one product to the other. It's basically an isomerization process. And with this as the intermediate. Okay? Now, any suggestion, what we're finding is that this product is more stable because at equilibrium it's 80% of that, 20% of that. So it's more stable, and I've got to put a hydrogen on to make sure that we don't change the situation. Why, or can you recognize from anything that you remember from last year that why this compound might be more stable than that one? Anybody have any notion? Remember when you were doing E1 elimination reactions? I'm sure that your professors told you that the more substituted double bond was a little bit more stable. So here we have a di-substituted double bond, here we have a mono-substitute. So using that idea, this should be a little bit more stable than that one because it's more highly substituted double bond. If you took time to look up a carbon to bromine bond on a secondary carbon is a weaker bond, less stable than the carbon to bromine on a primary carbon to bromine bond. So both ideas, and we only have to remember one. Probably the easiest one is the substitution pattern on double bond. Both of them suggest that, or at least allow us to feel comfortable that the thermodynamic product has the most substituted double bond. The kinetic product, the nucleophile, likes the carbon which is the most highly substituted. Okay? Pardon? The second idea is the carbon to bromine bonds. If you'd look up and say, this double bond prefers to be here than here. The carbon to bromine bond, this bond is weaker than that carbon to bromine bond. You can look it up. It's in your textbooks. It's a weaker bond because if you break that, you'll end up with a radical, and this radical is more stable than that radical. But just keep one of them in mind. The idea that this is more substituted, therefore it's more stable than that one. The double bonds can probably control more of the idea than the other one. Okay? Basically, once you have that in mind, then you can pretty well do any kind of prediction about what would happen when you take either a diene system plus an electrophile or an allylic system with a leaving group, and what would happen under thermodynamic, or what would happen under kinetic conditions. And just to, for you to sort of have the idea is, if I suggest the reaction is done at low temperature, you should say, well, that means we are working under kinetic conditions, kinetic control, and at high temperature, we're working under thermodynamic control. So, just do one more example, and a couple of illustrations, and then we'll go on to another topic. Pretty good question for an exam would be, predict the major product expected. Of course, I always ask, even though it's bloody hard to mark and take time consuming, I always ask you to explain why. And the question is, no, actually we'll turn it around. Explain, first of all, the following transformation. We start off with a tertiary alcohol. This